This is the Claisen rearrangement, and here I have the starting reactant and then heat and our final product. Here is our starting reactant, and from there, to start the mechanism, this double bond carbon here is going to swing down to the carbon in this ring, and then it will form two cyclic rings. And since this carbon is now fully substituted, the double bond here will resonate up here to the oxygen to fulfill the oxygen bond. And then now the oxygen is fully substituted, so this bond will resonate onto this side of the ring, which will also open up this cyclic ring. And now the oxygen has a negative charge since the bond left, but this double bond will resonate back down into the carbon ring, giving us our final product, changing the oxygen to an OH since it lost its bond. This is my predicted reaction coordinate diagram. Since this mechanism is exothermic, the products are lower than the reactants since energy is being released. The first transition state represents the second cyclic ring breaking, and the second transition state represents the double bond leaving the O, making the OH. You could speed up this reaction by adding a polar solvent, something like acetic acid, and you could also raise the temperature since this mechanism is converted thermally anyway. The recent literature that I found was titled Base-Mediated Cascade Rearrangements of Aryl Substituted Diallyl Ethers, which was written by Reed and others. And in this article, they reported their studies on the base-mediated cascade rearrangements of the diallyl ethers through 3 reaction mechanisms while using the same starting material and by altering the base and conditions. This is related to the Claisen rearrangement because the third mechanism they studied was the isomerization Claisen proto-desylation pathway. In the end, they developed and investigated the mechanism of the new base-mediated rearrangements and showed that the mechanism can proceed within a combination of mechanisms. The Claisen proceeds with some degree of dissociation since they are generally preceded via a concerted closed transition state. Here is the carbon-13 NMR for the starting reactant and the ending product. They both have a benzene ring about around 120 to 140-ish, and then a C double bond C around 100 ppm, and then the difference is the starting reactant has an O single bond C around 30 to 40 ppm, and the ending product has a C single bond OH around 60 ppm. This is the proton NMR for the starting reactant and the ending product. You can see that they both have a benzene ring again around 6 to 8 ppm, and then the starting and the ending again also have the CH2 hydrogen environment around 4 and 4.5-ish. And then the difference is that the ending reactant has a C single bond OH around 2 ppm. This is the predicted infrared spectra, and the main difference is that there's a 3200 to 3600 C single bond OH, and then the starting reactant has a 1050 to 1150 C single bond O.